Hi everybody. The last video I made about the signal generator that I have in my little electronics lab here was raising quite some interesting views. Even the supplier of the signal generator was showing some interest. Wow, I was surprised. I'm typically a consumer of materials of YouTube, but in this case I was a little producer of some content and I raised some interest. Actually, over the last few days, there was a question coming up. Can you use the JDS6600 to measure the frequency of a rig? And I take a rig as a transmitter. So I did a little bit of playing with that today, and I would like you to kind of show what I found there. First, let's just zoom in a little bit to the signal generator and get a little bit closer here on the bench. So there we are. And as you can see, hopefully that shows well, I have set the output of both channel 1 and channel 2 to 14.060 megahertz, sine wave, and an amplitude of 5 volts, that is, where you can see that I have the output of channel 2 in use, and it's through a coax cable loops back to the external input. And actually I hadn't been playing with this device as a frequency counter, to be honest. And I didn't show that in the video either, so it's about time to go that route. So I was playing a little bit with the user interface, and yeah, there is a wave and a measure button. And actually, if you go into the wave mode where you typically are, it works as a generator. But if you use the measure button, the output from the signal generator remains intact, but the display is showing you the option to measure frequency. And you get a screen that looks like this. And this is interesting stuff because it allows you to measure, and you can either measure or counter. And what I suppose is meant here is that in this case it's just counting the amount of pulses or signal it sees without resetting, and here it's in measure or in frequency counter. No, it's not a counter here, it's like a device that measures frequency. And you can adjust the gate time, which is currently set to 0.1 second, and it measures nicely 14.060.0102 megahertz. Well, it expresses it in kilohertz. It says 14.060.02 kilohertz. So it nicely points out the frequency generator is just looping back to the frequency measurement device here, and it is measuring the frequency it outputs. So yeah, it does work like that, and it actually works quite nicely. So what you may have noticed is that, well, I've put a splitter on here, and the signal also goes to my oscilloscope, which is next to the signal generator, as you can see here. And wow, the signal is nice here. And the reason I did that actually is that there is also a frequency counter in this Rigel DS1054C oscilloscope. I have connected the signal to channel number 1, and I'm measuring of channel number 1 here. And the hardware counter in here is also looking at channel 1, and I'm not completely sure if you can see that from a distance here, but it probably works like this, and you can see that it nicely measures 14.0601 megahertz. So yeah, clearly both tools measure the same thing. So would you be able to use these to measure the output of a transmitter? Maybe. before I went there, I did a little further experiment. A few years ago, I bought another frequency counter, and which is also in the lab here. And you can see that's over here, currently not connected. And what I can do is I can also take the signal from the devices into the, oh, come on, the plug doesn't want to come loose. Just hang on a second. Oh yeah, it's quite difficult to do this with all one hand, so I had to kind of get the coax connector loose, and now I'm ready to connect it to the signal generator, which has two inputs. One is for 0.01 Hertz to 50 megahertz, and the other one is for 50 megahertz to 2.4 gigahertz. And in this case we have a 14 megahertz signal, so we connect it to port number A. Let's just do that. There we are. And let's just see what it measures. Hey, no surprises. 14.0600 megahertz, completely as expected. So yeah, seems like we have a few different measurements done with different devices. They all give the same output. So conclusion clearly is that we can use this device to measure frequency. Let's do some further thinking if we could use this for measuring the output of a transmitter. And to see if we can measure the output of a transmitter with the signal generator / counter, I took a quick look in the JDS6600 quick guide PDF file, which I got with the device. I'm not even sure where I got it from, if it came with the device, if it was on the CD, or if I downloaded it somewhere from the internet. But it has a section in the document that has the external measurement function, and underneath that it says that the input signal voltage range should be between 2 volts peak to peak all the way up to 20 volt peak to peak, which is no surprise because that's pretty much what the device can generate from the signal generator part, so no surprises there. Now, what does that mean and how can we use this information? So I started scribbling a little bit. And if we would just imagine a 20 volt peak signal as an input on the device, that means that we would have a signal that should stay below 10 volt peak voltage, and that's peak voltage here. And if we want to bring that back to what we normally measure and calculate with, that's the effective voltage. That means we should stay and keep our signal on the inputs below the 7.07 volts. Okay, so if we would just consider a transmitter here, and have a transmitter which is sending its signal into a typical 50 ohm dummy load, it means that the signal on that line where we would just put our measurement device has to stay below that 7.07 volts. What does that mean exactly? Well, if we just take a little bit of a closer look at that and just consider that power equals voltage times current, considering a typical 50 ohm dummy load, that transfers to power equals voltage squared divided by 50. So what then becomes the maximum power that we would be able to transmit to not overload the frequency counter? Well, it shouldn't go over 7.07 volts. That's squared divided by the 50 ohm dummy load that we typically use in setups like that to make the transmitter happy. That means we shouldn't use more than 1 watt of energy out of the transmitter, which is typically not a lot. And then we're absolutely looking at maximum figures, because would we go above and beyond that, there is always a risk that we just damage our wonderful device. So could it be used for measuring the output frequency of a transmitter? Maybe. It would take a little bit more than that. Just hang on a second, let me get a device. And actually the device that I got into the picture here is something that I homebrew myself a couple of years ago. I call it a directional coupler. And this device might be a very handy thing to start measuring the output power, output frequency, and doing all kinds of stuff when measuring on transmitters. The topic of a directional coupler might be well beyond the topic of this video, and a little bit of Googling will show you lots of examples of how you can build such a directional coupler yourself, or how you can even just buy one straight from eBay maybe, but this one is kind of homebrew. Now what this device does, and the labels on the little box already give some hints here, is that it takes some input, which would typically come from a transmitter, which then is directly going to the output. So here comes the transmitter, the signal just passes through, comes out and goes to the dummy load on the other hand. So what are these two thingies at the bottom doing here? Well, it appears that in this little box there is a very light coupling between what is passing through here towards the ports on this side. And actually, if you just connect the transmitter here and a dummy load on that side, you can measure two different things on these ports here. It says reflected here and it says forward there. Well, if you would just go measure here, you would get a attenuated, a very small piece of the signal that goes in this direction coming out on this port, to the level where over here you're not missing the amount of energy that's going here. We're talking about an attenuation of approximately 30 decibels, so that's a very, very small fraction. Not only that, but it can look in both directions. So over here you can measure the signal that goes in that direction, whereas, as the name of directional coupler kind of gives away, if you want to see what signal is coming back out of the dummy load back towards the transmitter, you can measure that on the reflective port here, and measure all kinds of interesting stuff. Detail to mention here is that all ports should always be terminated with 50 ohms. So if you're having a transmitter here and a dummy load of 50 ohms here, and you would like to measure a frequency or the forward power, you would measure over here with a 50 ohm measuring device, and you would terminate this port typically with a 50 ohm stub, or a very small dummy load, or whatever you want to call that. And a device like this would typically be used to measure on a transmitter that puts out any substantial amount of power, rather than connecting it directly to your sensitive gear and taking the risk of damaging it, which of course we don't want. So to protect your signal generator / counter from too big inputs from transmitters, it's absolutely kind of encouraged to have a device like this in between to avoid things going terribly wrong and ruining your days. So I hope this information has helped you. Feel free to leave comments below. I'm not a very active monitor of that, but from time to time I take a look, and if there's any good questions, you might even trigger a new little video, because I think this is rather fun. Hope it helps you. Goodbye for now.